Let's actually do the proof from last time. I have it written right here. So the proof from last time, or finish up the proof we're talking about last time, goes like this. So first of all, let's define this sequence H. DF's defined. The sequence goes like this. We define H of 0 to be 1, H of 1 to be 2, H of 2 to be 3, and then we define H of k to equal H of k minus 1 plus H of k minus 2 plus H of k minus 3 for all k bigger than or equal to 3. So for H of 0, H of 1, H of 2, there's just initial conditions. They're just defined. But for all k bigger than 3, once the index is bigger than or equal to 3, we can discover what the sequence is based on this recursive formula. So this is a recursively defined sequence right here. And notice, right, recursion and induction both have this like self-generating nature to them, where you plug in a few initial conditions or base cases, and then there's some general step that can get you from previous cases to the next step, and you can keep generating from there. They keep feeding it back into itself. So this is like what the idea of recursion is. And so it's going to make a lot of sense that we're going to end up using an induction proof to prove something about this recursive sequence, because induction proofs are inherently recursive and the sequence is inherently recursive. But anyway, let's just refresh ourselves on what this is, just to give a practice. So to calculate H of 3, for example, using this recursive formula, what you do is H of k minus 1 plus H of k minus 2 plus H of k minus 3. This is just the sum of the 3 previous terms, right? Like if this is H of k, the one before it's H of k minus 1, the one 2 before it's H of k minus 2, on and on. So H of 3 will be the sum of the 3 previous terms. So that would be H of 2 plus H of 1 plus H of 0, which in our case, H of 2 is 3, H of 1 is 2, H of 0 is 1, 3 plus 2 plus 1 is 6. So that is, that's what H of 3 is. And then we do the same thing to calculate H of 4, H of 5, on and on and on, out to infinity. Anyway, so why do we care about this sequence? Well, there's a very interesting claim we can make about it. And the claim goes like this. Claim. For all n in x and z such that x is greater than or equal to 0. So for all n in this set right here, by the way, when I was talking about the idea of strong induction earlier, I might have accidentally had an n here instead of z. It should be a z, because z includes negative numbers, and there's no reason why you know, you don't say it's true for everything bigger than or equal to -5. It's totally fine to use negative numbers. But anyway, the claim is for all n greater than or equal to 0, we have that h of n is less than or equal to 3 of n, 3 to the n. That's totally our claim. And now let's just do an aside and talk about why we would think this is even true. I mean, we can try it out for a few examples, right? I mean, we can look at h of 0, and yeah, h of 0 equals 1, and 3 to the 0 equals 1. So 1 is less than or equal to 1. H of 1 equals 2, 3 to the 1, right? 3 to that index is 3, and 2 is less than or equal to 3. So we can do more and more of these, and we see it keeps working out. But the question is, how can we prove beyond any doubt that it will always work out? That we'll never, ever, ever be in a situation where it's not true? That's a trickier question, right? That's a very tricky question. But luckily, we have a very tricky solution, and that is strong induction. So here's the idea. I'll write it down. If we can prove that whenever the 3 previous cases hold or are true, the next case will be true, we're done. So by strong induction, if we can prove that whenever the three previous cases follow this claim, right, follow the claim that h of n is less than or equal to 3 at the end, follow this idea. Sorry, choking on almonds again. No, anyway, if we can prove that whenever the three previous cases satisfy the claim, that the next case will satisfy the claim, well, then we'll be golden because these three cases satisfy the claim, right? We already showed h of 0 is less than 3 to the 0, h of 1 is less than 3 to the 1, h of 2 is less than 3 to the 2. That all works. And if we can show this, that whenever the three previous cases are true, the next case will be true, well, then what we're showing is that, well, it's like these three cases are true, so the next case, h of 4, should be true. And in the next case, h of 5, since we show that h of 4, h of 3, h of 2 are true, will be true. In this case, h of 6, which h of 5, h of 4, h of 3 are true, will be true. This is the chain reaction. This is the old-timey car crank that keeps things moving forever, proving that this claim is true for all n, greater than or equal to 0 at least. So that is the idea. So what we really want to show, that for all, so we eventually want to show that claim is true for n plus 1, assuming claim is true for n minus 1, and n minus 2, because those are the three previous cases. I hope this is making sense. So the idea is, once again, to prove the next case just from the truth of the previous cases. And if we can do that, and we have the base cases, strong induction will take over this chain reaction. So if we want to show the claim is true for h of n plus 1, that means we really want to show that h of n plus 1 is less than 3 to the n plus 1. That's what it would mean if the claim is true. So let's check it out. So notice that h of n plus 1, well, what's that equal? Can we write that in terms of the previous cases? Because that'll really be helpful. And it equals h, so the three previous cases from n plus 1 are going to be n plus n minus 1 plus h of n minus 2, like I said there. So that's what h of n plus 1 is. It equals that. And so I kind of said this backwards. First I wish that's the other way around. Whatever. The point is that from this we can see why we care about the three previous cases. Because maybe if we can show the claim is true for all of these, then we'll be able to somehow in a roundabout way be able to show the claim is true for this guy. So anyway, assuming the claim is true, so if claim true for n minus 1, n minus 2, then we'd get that h of n is less than or equal to 3 to the n, h of n minus 1 is less than or equal to 3 to the n minus 1, and h of n minus 2 less than or equal to 3 to the n minus 2. That's just what it means for the claim to be satisfied for these three h's. And so in the formula here, since h of n plus 1 equals h of n plus h of n minus 1 plus h of n minus 2, it's certainly going to be less than or equal to, going off the screen a little bit. It's certainly going to be less than or equal to 3 to the n plus 3 to the n minus 1 plus 3 to the n minus 2, right? We just replace everything here with something that's bigger. But we eventually want to somehow get this to be less than or equal to 3 to the n plus 1. That's what we want to do, right? We want to show that that h to n plus 1 is less than or equal to 3 to the n plus 1. This is the time in class where I took a long pause and asked if anybody had any suggestions. If you have them, yell at the screen right now. The point is, we have to figure out some way to relate these three guys to this. We really want to show it's smaller. Here's the thing to notice. thing to notice is that I'll say notes. Three to the n plus one, right, equals 3 to the n times 3 to the 1. That's just an exponent rule. And then 3 to the n to 3 to the 1, well, I'm just going to change the order here. That's just 3 times 3 to the n. And what's 3 times 3 to the n mean? If we don't overthink it, it's 3 to the n added to itself 3 times. So this is just 3 to the n plus 3 to the n plus 3 to the n. Now we're cooking. These two look really similar, right? They're both an addition of 3 powers of n, just this one has the powers being n minus 1, n minus 2. This one has n, and n. But what's the thing you notice? The powers here are always bigger. They're always bigger. And note that 3 raised to a bigger number is bigger, right? 3 raised to n is bigger than 3 raised to the n minus 1. 3 raised to n is certainly bigger than 3 raised to the n minus 2. Because 3 to the n minus 2, 3 to the n is 3 to the n minus 2, and 2 more additional powers of 3 above that, right? So the point is that, I'm gonna avoid this glare. I'm gonna go under it. Ooh, I never saw that coming. The point is that now we can say that this is less than or equal, 3 to the n is less than or equal to 3 to the n. 3 to the n minus 1, that's again less than or equal to 3 to the n, because 3 to the n is a bigger power of n, or bigger power of 3. 3 minus 2 again is less than or equal to 3 to the n, because 3 to the n minus 2 is a smaller power than 3 to the n. But then we can do this exact math that we just did. 3 to the n plus 3 to the n plus 3 to the n, that is 3 times 3 to the n. And that just equals 3 to the n plus 1. So if we follow this out, we see that if we assume the claim is true for the 3 previous cases, then we can prove the claim will be true for the next case. If h of k is equal to 3 to the k for the 3 previous things before n plus 1, then the h of n plus 1 must be less than or equal to 3 to the n plus 1. It just has to happen. And this is exactly what we want to prove, or we want to show. This is the thing we needed to show to really do proof by strong mathematical induction, right? Because basically what this shows is that if the claim is true for everything up to n, then it'll be true for n plus 1. And that's all we need to show. Once you get the base cases all sorted out, then this self is keep feeding this back into itself, and it keeps proving us more and more and more and more cases for free. So, any questions? Sadly, you can't ask me. But anyway, I'd pause it if you needed to see that more, think more. Feel free to email me if you have any questions on these kind of things. Let's go down to business actually trying to prove this. So, still proof. And the proof is by strong mathematical induction on n. And so we always start with the base cases. But there's a very interesting question of how many base cases we needed, right? And we said earlier, right, when we were talking about strong induction, I say right a lot when I have no one to bounce ideas off of. We said earlier that the number of base cases you need depends entirely on how many previous cases you need to be true in your argument. And so let's think about this. So our whole idea, right, was that h of n plus 1 equals h of n plus h of n minus 1 plus h of n minus 2. And we can eventually show through a chain of these less than or equal, that's less than or equal to 3 to the n plus 1. That's kind of what we did on this side. But that's not always true. right? I kind of hid a thing in here, right? This is not always true. This isn't true for h of 0, for example. H of 0 doesn't equal h of negative 1 plus h of negative 2 plus h of negative 3. This recursive formula only applies when k is equal to 3, when the index is bigger than or equal to 3. But we need to use this recursive formula to do our proof that h of n plus 1 is actually less than or equal to 3 of the n plus 1. So in order for this inductive step to take over, in order for our argument to work, we need n plus 1 be greater than or equal to 3. We want this index to be greater than or equal to 3. But then subtracting 1 from both sides, that means we need n to be bigger than or equal to 2. So this works as long as n is bigger than or equal to 2, right? That is when the inductive step kind of starts taking over. And so what that means is that everything up to 2, we need to verify with base cases. Because even though, like I said, it starts at 2, what that means is we can use everything up to 2 to prove that it's true for 3, to prove that P of 3 is true. And so that means the first thing we can actually prove using induction, the inductive step in the previous cases, is 3. That's true for 3. And so we need to prove everything up to 2 manually. But after that, this whole argument just takes over automatically and proves everything. So let's get going. Oh, it's a beautiful voice sometimes when I'm alone at night. So base cases. So what I just said is that we needed to prove everything up to 2. And so let's go ahead and say let n equal 1. We need to prove the claim is true for 1. What's the claim again? It's that h of n will be less than or equal to 3 of the n. IKA, in this case, we want to show h of 1 is less than or equal to 3 of the 1, which I already did. Actually, no, I'm sorry. We don't want to start at 1. We want to start at 0, right? Because, right, our set starts at 0. We're trying to prove if everything bigger than or equal to 0. Let's go ahead and let n equal to, let n equal to 0. Note, h of 0 equals 1 by definition. Further, 3 to the 0 equals 1. Thus, h of 0 is less than or equal to 3 to 0. Done. That easy. Right? Now, that's for 0. Let's do 1. So 1, again, we're trying to prove that h of 1 is less than or equal to 3 to the 1, trying to show the base, the claim holds for 1. So let's go ahead and note that h of 1 equals 2. And further, 3 to the 1 equals 3. Since 2 is less than 3, h of 1 is less than or equal to, let's say less than or equal to here. H of 1 is less than or equal to 3 to the 1. Then we can do the same thing for the last case, n equals 2. And I'll say note, h of 2 equals 3 by definition. Further, 3 squared equals 9. Since h of 2, 3, is less than 3 squared, which equals 9, h of 2 is less than or equal to 3 squared. So we just proved that the base case holds for, or we just proved that the claim is true for all these base cases. So I'll say hence the base case holds. Make sense? Normally I'd write this into the base case holds, by the way, below, but just say to save some space on this very limited space whiteboard. I'm going to do that to the side. Anyway, though, let's do our inductive step. So the inductive step, remember, is how you prove, well, I'll show you what we want to show. The inductive step, here we want to show that for all n greater than or equal to 2, we say, because that's when our argument's going to work, as we argued, for all n greater than or equal to 2, p of 0 can start at 0, and p of 1 all the way out to p of n will imply p of n plus 1. So the idea being, the inductive step, we want to show that everything up to n holds, know, the next case will hold. And then you know, then that means the next case will hold, 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 chain reaction. As we want to show, in this case, i.e., want to show that for all, we want to show that, yeah, for all n greater than or equal to 2, if h of k is less than or equal to 3 to the k, for all k such that 0 less than or equal to k less than or equal to n, then h of n plus 1 less than or equal to 3 to the n plus 1. This is just writing out exactly what this is saying. It's saying that for all n greater than or equal to 2, we want to show that if it holds for everything between 0 and n, everything up to n, then it'll hold for h of n plus 1. H of n plus 1 will be less than or equal to 3 to the n plus 1. This is the big idea we want to show. So let's just do it. So remember, to do this, this is a universal conditional statement we're proving in this inductive step. So to do this, we're going to want to, I don't like this. This is like 2 periods. It's actually just a smudge, but you know what? We'll pretend it's the period. I feel better now. Anyway, so let's go ahead and let n be any arbitrary / particular integer such that specifically n is bigger or equal to 2, because that's when our inductive step takes over. Now, we want to show that h of n plus 1, oh, I'm sorry, I'm getting ahead of myself. Now, for every n greater than or equal to 2, we want to show that if the claim holds up to n, it'll hold for n plus 1. So here's when we make what's called the inductive assumption. So assume that for all k and z such that 0 less than or equal to k less than or equal to n, we want the claim to be true. We want hk to be less than or equal to 3. Okay, there we go. Sorry, got distracted. So we want to assume that the claim holds for everything up to n, everything between 0 and n. And this right here, this is what we call the inductive assumption. Assuming the claim holds for everything up to n is called the inductive assumption, or, depending on where you are in the country, the inductive hypothesis. It actually might not be a country thing. It's probably not slang. It's probably a department-to-department thing, or maybe even a person-to-person thing. This is your personal choice. Inductive assumption, hypothesis, whatever you want. But if someone mentions an inductive something like this, you know what they're talking about. It's this thing that we assume. All right. So this is the big thing we assume. We want to show that h of n plus 1 is less than or equal to 3 to the n plus 1. That's the big idea. So let's just get cracking, right? The whole idea in our side that we like a long time ago that we were using trying to prove this, the whole thing was that we want to write h of n plus 1 in this form right here. And then we can start dealing with the previous cases and everything will work out. But remember, this only holds as long as the index is bigger than or equal to 3. So first we need to show that n plus 1, that index, is going to be bigger than or equal to 3. And then we can use that, we can use the recursive formula on h of n plus 1. Otherwise, we don't know we can use it. So what I'm going to say is note, since n is greater than or equal to 2, n plus 1 is greater than or equal to 3, by adding 1, that's not 1, it's a triangle, 1 to both sides. All right. So now that we know that n plus 1 is bigger than or equal to 3, we can use the recursive formula on it. thus, by definition of the H sequence, H of n plus 1 is going to be the sum of the three previous terms. So it's going to be H of n plus H of n minus 1 plus H of n minus 2. And notice, by the way, this didn't accidentally happen that n plus 1 is greater than or equal to 3. We specifically chose our n to be bigger than or equal to 2, so we added 1, we get to be bigger than 3, so we could do this. Like back when we were deciding how many base cases we needed, this is exactly what we did. We asked ourselves, what do we need to make n bigger than or equal to ensure n plus 1 is bigger than or equal to 3, so we can use this recursive formula. This is by design. Anyway, anywho, what do you want to say? Transition. We have this. And then remember in the aside, we were saying that, hey, as long as the claim holds for the three previous cases, this will be 3 to the n, this will be less than 3 to the n, 3 to the n minus 1, 3 to the n minus 2, and then we can go from there and prove this whole thing will be less than 3 to the n minus 1. That's the idea, at least. But in order to use that, in order to say that the claim holds for these, we need to make sure that n minus 1 and n minus 2 are actually in this range between 0 and n, because our inductive assumption just assumes that it works up to n. So even though it seems obvious, we have to prove that n minus 1, and n minus 2 are all in this range up to n. So what I'm going to say is note that since n is greater than or equal to 2, which is greater than or equal to 0, n is greater than or equal to 0, and since n is greater than or equal to 2, n minus 1 is greater than or equal to 1 by subtracting 1 from both sides, which is greater than or equal to 0, and since n is greater than or equal to 2, n minus 2 is greater than or equal to 0 by subtracting 2 from both sides. Thus, n is greater than or equal to 0, n minus 1 is greater than or equal to 0, and n minus 2 is equal to 0. So the point is they're all bigger than 0, which is good, because to be in our range where the inductive hypothesis holds, where we assume that the claim is true for everything up to n, we need these k values, these things right here, to be between 0 and n. So we know they're bigger than or equal to 0, which is good. Further, and once again, I'm going to go below the glare. Yeah. So further note, let's just get the whiteboard. So further note that n is less than or equal to n, n minus 1 is less than or equal to n, and n minus 2 less than or equal to n. That one's easy. It's really easy to show that n minus 1 and n minus 2 are less than or equal to n, that they're not up to n. It's a little harder to show that they're actually, that the lower bound thing works, but it's kind of obvious that it works anyway. But anyway, we need to prove it. So thus what this proves is thus, or I'll say hence, use thus too much already. Hence, we have that 0 is less than or equal to n, less than or equal to n, 0 is less than or equal to n minus 1, less than or equal to n, and 0 is less than or equal to n minus 2, less than or equal to n. Oh, no, I meant to put it in here. There we go. That wouldn't make any sense. If 0 is less than or equal to something, if 0 is less than or equal to n minus 2 less than or equal to 0, that would mean n minus 2 equals 0, but let's squeeze through. But anyway, actually that's not the squeeze through, technically, but it's close. Anyway, the point is we've just shown that n minus 1, and n minus 2 are all in this range up to n, and we're assuming by our inductive assumption that everything up to n holds, and from that we want to show that n plus 1 holds. So that the claim will be true for n plus 1. So I'll say thus this time, by our inductive assumption, I'm really going to wear this word out today, by our inductive assumption, since these are all in the right ranges, h of n is less than or equal to 3 to the n. H to the n minus 1 is less than or equal to 3 to the n minus 1. H to the n minus 2 is less than or equal to 3 to the n minus 2. And here's where I normally say etc., but that's where we can stop because that's all we care about. We just care about showing the 3 previous cases are less than or equal to 3, or less than or equal to their respective powers of 3, and they totally are under the assumption hold up to n, which is our assumption, which is how induction works. So, if we put that together, then h of n plus 1, then we have that h of n plus 1 equals h of n plus h of n minus 1 plus h of n minus 2 by the above. And then h of n, well, that just equals what? Oh, h of n, I'm sorry, not equals. This is going to be less than 3 to the n plus 3 to the n minus 1 plus 3 to the n minus 2. We can say that because we just showed above that h of n is less than 3 to the n, h of n minus 1 is less than 3 to the n minus 1, h of n minus 2 is less than 3 to the n minus 2, on like that. So we just showed this above. And I'll say, since we showed h of n less than or equal to 3n, h of n minus 1 less than or equal to 3 to the n minus 1, and h to the n minus 2 less than or equal to 3 to the n minus 2. All right. So we know that h of n plus 1 is going to be less than 3 to the n plus 3 to the n minus 1 plus 3 to the n minus 2. And here's where the aside comes in. I believe it was Patrick in class who came up with this part. And that is, remember, that since n is bigger than n minus 1, 3 to the n is bigger than 3n minus 1. It's a bigger power of 3. Same thing with 3n minus 2. Therefore, this is 3 to the n, less than or equal to 3 to the n plus 3 to the n plus 3 to the n. Because 3 to the n is less than or equal to 3 to the n, 3 minus 1 is less than or equal to 3 to the n, 3 minus 2 is less than or equal to 3 to the n, on and on like that. And this is since 3 to the n minus 1 less than or equal to 3 to the n, and 3 minus 2 less than or equal to 3 to the n. We can also say 3 to the n is less than or equal to 3 to the n, but it's kind of just we copied it, so it's fine. But then what does this equal? Well, this equals, and actually I want to have these guys here. Just kind of showing how the flow of the argument works. What I wrote down is true. I just kind of like this better. It's like this equation leads to this inequality, leads to this inequality, leads to this following inequality. The following inequality is going to be that, well, 3 to the n plus 3 to the n plus 3 to the n, that is just 3 copies of 3 to the n. And what is 3 copies of 3 to the n but 3 to the n plus 1? Boom! Boom! That's totally how you do it, right? Oh, it's actually kind of perfect, so you can just see the inductive step right now in the proof. So what we, in the screen, so what we just showed right here is that if the claim is true up to, if we're all in greater than or equal to 2, if the claim is true for all things up to n, then it'll be true for n plus 1. So in particular, 2 is bigger than or equal to 2. And by our base case, right, the claim is true for everything up to 2. Therefore, by modus tollens, if you want to bring that back, the claim is true for 3. And then, since it's true for 0, 1, and 2, by the base case, it's true for 2 by the thing we just did, true for 3 by the thing we just did, it's true for everything up to 3. Therefore, by this argument, the claim is also true for 4. It's true for everything up to 4, so then it's also true for 5, 6, 7. This is the domino effect. This is the chain reaction. You just keep feeding this back into itself and just keeps popping out more and more and more and more and more and more and more answers, making our conclusion that is that for all n, I'll say therefore, for all n, and the set we're talking about want to be bigger than or equal to 0. That's what we had up here. So for all n in x and n, such that x is bigger than or equal to 0, h of n is equal to 3. Since you proved the inductive step and we proved the base case and the overlap there, that's everything you need to show the claim's always true. Done. And that wasn't that hard, I don't think, right? I mean, this was long. It took an entire whiteboard and a lot of desks. Oh, look at this for this little thing. But I thought it was worth it. I think really a lot of it's just structure, right? I mean, like proving every line here in the red is easy. The base cases are really easy to prove. It's just verifying things. And in the beginning of this is just standard strong induction, right? Let n be any arbitrary integer such that n is greater than equal to 2, making sure that the base case overlaps here. Assume that the claim is true for everything up to n between the first case we care about and n. And then we want to show that it's true for n plus 1. And then here's where we start getting a little bit creative. But we've seen things like this before, where we kind of note the index and say, oh, okay, n plus 1 is this index, therefore we can use a certain recursive formula, and on like that. But this is where the creative part of a strong induction proof comes in. But I think you guys totally got this. So that's that. Imagine a pause right here. Actually, there'll be probably a literal pause if you guys are watching this on the Canvas page. But anyway, if you're not, if you're watching this YouTube page, imagine a pause right here.